Hello everyone, in this video we're going to be looking at the natural log function. Okay, and logarithmic functions. Okay, so we'll probably do integration of exponential functions later, because this lesson is a big one. Okay, so a logarithmic function is a function that is defined in terms of a logarithm. F of x equals log base b of x, where b is a real number. Okay, so just in case you were forgot, log base b of x is equal to c if b to the c equals x. So basically the logarithm gives you an exponent, okay, the exponent that you need to raise the base to get this number x, okay? Now, if you remember there are lots of log properties that you need to remember, okay? So this should be kind of reviewed. Log base b of a times c equals log base b of a plus log base b of c. Now, log base b of a over c equals log base b of a minus log base b of c. Now log base b of a to the c equals c times log base b of a. Okay? And a to the log base b of a equals a to the log base b of, it's not a, sorry, b to the log base b of a equals a. Okay, it's a bit confused over there, but we're fine. Okay, and log base b of b to the a equals a. Okay, so we have all these properties, but we're not going to focus on the generic log function. We're going to focus on this one over here. The natural log function equals ln of x. In case you don't remember, the ln function, natural log function, is the log base e of x. Okay? So it tells the exponent you need to raise e to get x. And the ln function is connected to e, so you know, just based on last video, that something exciting is going to happen in terms of calculus. Okay? So what we're going to do is take the derivative. Okay? So technically, if f of x equals ln of x, what's f prime of x? Now, we proved the derivative of e to the x last video, so we're going to allow the usage of the derivative of e to the x. So we know that the derivative of e to the x equals e to the x. We proved it last video, so it's valid. So let y equals ln of x. And now what we're going to do is use implicit differentiation, okay? So we can solve for x as x equals e to the y, okay? Now if we take the derivative of both sides, okay, with respect to x, what do you get? Well, you get 1 equals e to the y times dy dx. Derivative of e to the x is e to the x. And we're just doing this implicitly. So if we solve for dy dx, we get dy dx equals 1 over e to the y. Now we want it in terms of x, so we have 1 over e to the, well, you defined y equals ln of x, so e to the ln of x okay? And that is equal to x, so we get 1 over x. So the derivative of ln of x is 1 over x, okay? And this is important, okay? Because you have an irrational function that suddenly gets turned into a rational function, okay? So it's just as amazing as the e to the x derivative, okay? You have the simple function representing the derivative of a much more complex function. So let's see this in action. Let's find a derivative of ln of x to the fourth plus 27. Now that is equal to, we can use the chain rule over here. Okay, so that's 4x cubed over, okay, because this is a rational function. This will be a rational function. So we bring x to the fourth plus 27 to the bottom. This is our derivative. See, nice and simple. Now, we don't usually do derivatives of this type, okay, because they're not interesting. But ln is very, very, very useful in figuring out derivatives of complex looking functions that can otherwise be simplified using the log, okay, and properties of logs. So let's define f of x equals the cube root of x squared plus 5 over 3x minus 2. Take the derivative. Now this is a nightmare to integrate. You can use the chain rule and integrate it like that, but you know, it would not be the best choice. So what you would do is perform something called logarithmic differentiation, where you basically exploit the properties of logs and the ln function to help turn a hard derivative into an easy one. Let's see what I mean. So let y equals the cube root of x squared plus 5 over 3x minus 2. Now let's take the ln of both sides. Okay, so ln y equals ln of the cube root of x squared plus 5 over 3x minus 2. Now, this becomes 1/3, okay, since the cube root is the same as raising the expression to the 1/3 power. So 1/3 ln of x squared plus 5 over 3x minus 2. Now, because we have a quotient over here, we have 1/3 times ln of x squared plus 5 minus ln of 3x minus 2. So look what we're doing. We're using simple log properties, and now this derivative can be evaluated much easier. Okay? Now, what we can do here is excuse me. What we can do here is do this. Times, well, 2x over x squared plus 5 minus 3 over 3x minus 2. That equals ln. Okay, so we took the derivative. Okay, so from here we took the derivative. Now remember, we also have to take the derivative of the left side. Okay, we're basically turning this into an implicit problem. Okay, so this equals 1 over y dy dx. Okay, and now you can multiply both sides by y, and you get 1/3 times the cube root of x squared plus 5 over 3x minus 2 times the quantity of 2x over x squared plus 5 minus 3 over 3x minus 2. So we turn this crazy looking derivative into something much, much easier, okay? And you can use logarithmic differentiation in crazy looking expressions like this, or crazy looking expressions like this. This one's a fun one. F of x equals x to the x. Okay, so no power rule in this case, okay, since both the base cannot change. Okay, if you want to, well, the base has to change, but the exponent cannot change if you want to use a power rule. Nor can the base change if you want to use an e to the x or maybe turn it into a different form. So what do? There are two ways that you can do this. Okay, let's do method 1 with the log. So you have y equals x to the x. Okay, so you can take the ln of both sides. So you have ln of y equals ln of x to the x, and that in turn equals x times ln of x. We're just taking the exponent and putting it to the front of the natural logarithm. Okay, and if we take the derivative of both sides, you have 1 over y dy dx equals, now we just have the product rule, f prime g plus g prime 1 over x f. So times x. So x over x equals 1. And we basically multiply by both sides by y. So y times ln of x plus 1. And we solve that, sub in for y, we have x dx times ln x plus 1. Now here's an alternate method, okay? So let's say we have f of x equals x to the x. Now x, you can rewrite as e to the ln of x. Okay, so we have e to the ln of x to the xth power. Now this equals e to the x ln of x. Okay? Which, if you use the chain rule, you have e to the x ln of x. So the derivative with respect to this times the derivative of this inside function. So that's f prime g, g prime f. Okay, so if you did it, you get ln of x plus 1. And now we can express this in a simpler form. Okay, so if e to the ln of x to the x power times ln x plus 1, and that gets to x to the x times ln x plus 1. So both ways are good, okay? So you can see how that you don't have to use logarithmic differentiation, but it usually makes evaluating and finding derivatives a whole lot easier. A whole lot easier. So suppose we want to find, suppose we want to find the minimum value of this, or a maximum, any extrema, okay? So this function is only defined for positive real numbers greater than 0. Actually, positive real numbers, not 0. How does it get ln of 0? And that doesn't make sense. Okay, so now we have the derivative. We just set ln of x equals -1, which throws off some people. It used to throw me off because you might think this is undefined, but this function is only undefined if x is -1, not the actual logarithm. So you can raise both sides, okay? So you put e to the ln of x equals e to -1, and you get x equals 1 over e. Okay, so and you can check over here that this is indeed a, if we do 1 over e is about 0.367. So if we do 0, well, it doesn't exist as 0, or let's do 1. So ln of 1 is 0 plus 1 is 1. Now 0.1, okay, 0.1, ln of 0.1 is negative, well, it's less than -1, okay, since ln of 1 over e is -1. So this will be negative. So this is minimum value. So you get the minimum value is 1 over e, comma, the e through of 1 over e, or 1 over e raised to 1 over e's power. So this is your minimum value of this function, and this is a derivative. It's not much about ln of x except with these neat tricks that you can use to simplify derivatives. If you have any questions, please comment below, like this video, and share this video and pass it on. Thank you.